Okay, I'm turning on the recording now. So if you
Hello, Dada.
hi Dalman, how are you?
I'm fine, and you?
Fine, I'm great. Thanks.
Okay.
Good. So so now at this point, please type your name into the chat, even if you did already, because at this point it will be recorded so that I can save the names for later. Okay, so just do it at some point during the class, and we'll have a record of it for your attendance to make sure that you can keep getting your data. Okay, great. So I hope everybody's doing fine. Okay, it looks like we have somebody new. And Mr. Randolph, it's good to see you here. And okay, so this is good. I think we have a special guest today. So welcome Gongloa. And some people are still figuring this out on the chat. Yes, class now. Okay. All right. So I want to just review. We're gonna kind of finish up this this unit on matrices and geometry today, and then we'll start talking about some more calculational aspects of matrices. So the first thing I want to do is recall that we did this formula last time. So I'll draw a picture, but the point of the formula was that if alpha was an angle and we had a line through the origin that made an angle of alpha with the x-axis. So let's try that. Oh, let me delete that. Let's try this one more time. Yeah, great. So we have a line through the origin that makes an angle of alpha with the positive x-axis. Then what we did last time was we derived this matrix that gave you the formula for how to reflect a vector over that line. Okay, so for instance, if I have a vector v here, if this is my vector v, then I can look at its reflection over the line, which I'll draw in a different color. I'll draw it in red. This is the reflection of v over the line L. And what this matrix does that we saw last time is that if you multiply this matrix by v, then it gives you the reflection. So in this case, this vector over here in red is going to be a times v. Okay. So, and this was the formula that we had for doing it. So if you know what angle your line makes with the x-axis and you know what your vector is, you can calculate the reflection. Okay. So we did a couple of examples of this. I mean, there are a couple of examples of this in the homework, which we'll go through, but I just want to recall that we have this formula that's maybe not so easy to memorize, but it's not that hard to look up. So here, let me just write out in words, AV is the reflection of V over the line L. Okay, so one more time, a reminder, if you haven't yet done so, to please write your name into the chat so I have a record of attendance. It looks like most people have, but if you haven't, just write it in so that I know who's here. Okay. All right, so this is the main result that we had last time. We got this matrix that tells you how to reflect over a line, and the only input you need is the angle that line makes with the x-axis. Okay, and the matrix is a little bit complicated. It involves cosine and sine with these formulas that are not necessarily so easy to remember, but I mean, okay, this is what it is. Okay, so any questions so far? We're going to go over the homework examples. Oh, and this should say, of course, formula. It's a typo. Okay, formula. Okay, so let's look at the homework examples. So problem 1, we want to calculate what is the matrix of reflection over the line y equals x. Okay, so we have a very specific line, which is the line given by y equals x, which looks like this, right? So this is the line y equals x. This is the x-axis. This is the y-axis. And so we need to write down what the matrix is. So, well, we already know how to write down the matrix as long as we know what the angle is that the line makes with the positive x-axis. So the question is, what we need to do is fill in what this angle is, and then we can apply the formula. So what is the angle that the line y equals x makes with the x-axis here? We want to know what's the right angle alpha for this case. So does somebody want to answer what this angle should be?
Yeah,
Prince?
let me
Yep.
can we say 45 degree?
Yep, that's right. 45 degrees. Great. So it's exactly 45 degrees, right? Because this line is exactly in the middle between the y-axis and the x-axis. So it splits the 90-degree angle into two pieces. So it's going to be 45 degrees. Great. Okay, so now let's use this formula. I'm just going to copy it over. I just want to, wait, no. Sorry. Well, at some point I'm going to learn how to actually copy and paste, but for now I'm just going to rewrite the formula. So the formula is that the matrix A is equal to cosine squared alpha minus sine squared alpha. And then we have 2 sine alpha cosine alpha. And then we have also 2 sine alpha cosine alpha. And then we have cosine squared alpha minus sine squared alpha. Okay, so this was the formula. And now what we have is, in our example, as Prince said, alpha is equal to 45 degrees, right? Alpha is equal to 45 degrees. So we just have to plug that in. So what are we going to get? So A is going to be, this matrix is going to be cosine squared of 45 degrees minus sine squared of 45 degrees. And then 2 sine of 45 degrees, cosine of 45 degrees. And then here 2 sine of 45 degrees, cosine of 45 degrees. And then lastly, cosine squared of 45 degrees times minus sine squared of 45 degrees. Okay. Sorry, that should be degrees, not a square. Okay. Okay, so let's write down our values. So what do we know? We know that sine of 45 degrees and cosine of 45 degrees are what? Yes, Gabriel?
Yeah.
Yep. Yeah. Square root of 2 over 2 and it's also the same. Great. Thank you, Gabriel. Okay. So sine and cosine of 45 degrees are both square root of 2 over 2. So let's fill it in. Let's see what we get. Well, we get that this is so here the cosine and the sine are the same, right? So these differences are both going to be 0, right? So we're going to get a 0 here and a 0 here. And then, well, these elements are the same. These entries are the same. So sorry, I'm just going to mute because there's a lot of background noise. Sorry, I have to mute because there's a lot of background noise there. But 2 times sine 45 times cosine 45, as Gabriel said, this is going to be 2 times square root of 2 over 2 times square root of 2 over 2. And this over here is also going to be 2 times square root of 2 over 2 times square root of 2 over 2. So this whole matrix actually just simplifies to 0. And then this becomes what? 1, exactly. So this becomes 1. And then this is the same thing. This becomes 1 and this becomes 0. Right? So this is the matrix. Sorry, again, I need to mute because it's very loud. So this is the matrix. The matrix is 0, 1, 1, 0. And we want to just check that it sends this vector AB to a vector BA. And so what's our check? I'm just going to write it over here because we don't have that much extra space. So check, if I take 0, 1, 1, 0, and I multiply it by the vector AB, well, this is Well, I get A times the first column plus B times the second column, if we use the column method, right? So this is going to be A times 0, 1 plus B times 1, 0. And that's the same thing as 0A plus B0. And that's the same thing as BA, right? So this is what the example said, right? We want to show that it sends AB to BA. And this is right, you know, for reflecting over the line y equals x exactly interchanges the y coordinate and the x coordinate, right? So if I start with a vector here, that's, I don't know, let's say this vector is 1, 3, then its reflection over the line y equals x is going to be exactly the vector 3, 1. Okay. So we see that this interchanges the x and the y coordinate, and we see how that comes from this formula when you plug in alpha equals 45 degrees. Okay, so you plug in alpha equals 45 degrees, this matrix becomes very simple. It just becomes 0, 1, 1, and 0. Okay, so that's how homework problem number 1 works. All right, any questions?
Yeah, sure.
Yes, question?
Yeah, it's Prince.
Yes, Prince.
Yeah, to where we have a 2 times root 2 over 2. So was it 2 of the roots were multiplied to give 4 and divided by 2 is what equivalent to 1?
Exactly, right? So here we have, in the numerator, we have 2 and a square root of 2 and square root of 2, right? So that all multiplies to 4, right? Because we have 2 and then square root of 2 gives you 4, right? So you get a 2 and a 2 is 4. And then in the denominator, we also have a 2 and a 2, and that's going to give 4. So when you simplify everything here, you get down to 1.
So yeah, sure. And if for each thing it will looking like this, we only have root 2 over 2 times root 2 over 2.
Right.
How was the numerator of the root were going to be? Was it going to be multiplied, or was it going to be choosing, like we want to be choosing from there?
Right. So if you didn't have the 2, if you had the root 2 over 2 times root 2 over 2, we would just multiply the numerators to get 2, and we'd multiply the denominators to get 4. So that would just be 2 over 4, which would be the same as 1 over 2.
Oh,
Okay.
okay.
All right. Good. Other questions? Okay, so let's do the next problem. So the next problem says, consider the line y equals square root of 3 times x. And we want to know, what angle does this line make with the positive x-axis? And then we want to know, what's the vector that's obtained when 1, 1 is reflected over this line, right? So let's see what we've got here. I have the line y equals square root of 3x. So that's kind of like this. So this is y equals square root of 3 times x. This is the x-axis, this is the y-axis. And we want to know, what is this angle here that this is going to make with the positive x-axis? Because ultimately, we want to know what happens when we reflect a certain vector over that line. And in order to do that, we need to use the formula. But to use the formula, we need to know what the angle is, right? So does anybody know how to calculate this angle right here? It's 60 degrees. That's right. Thank you, Gabriel. Yeah, so this is exactly 60 degrees. How do you know it's 60 degrees?
From the trig ratio.
Right, exactly. So this comes from the trig ratios, because if you have this y equals square root of 3x, then you can build a triangle here. Sorry, you can build a triangle here where one side of this is equal to 1 and the other side of this is equal to square root of 3. And then if alpha is the angle, you get that the tangent of alpha is equal to square root of 3 over 1, which is equal to square root of 3. And this tells you that alpha is equal to 60 degrees. Okay, so the line y equals square root of 3x makes this angle 60 degrees. okay? Because you can, the y coordinate is square root of 3 times the x coordinate. So the ratio of the two sides of this triangle will be square root of 3 to 1. And that corresponds to an angle of 60 degrees over here. So now that it's 60 degrees, we can form the matrix again. So now, form the matrix of reflection. So I'm just going to go back. We'll see we have this formula over here, but now I'm going to plug in 60 degrees instead of 45 degrees because it's a different line. Okay. So I'll do this with 60 degrees. We have the matrix. Ooh, no. Sorry. Okay. So the matrix is going to be cosine squared 60 degrees minus sine squared 60 degrees. And then 2 cosine 60 degrees sine 60 degrees. And then 2 cosine 60 degrees sine 60 degrees. And then sine squared 60 degrees minus cosine squared 60 degrees. So again, one more reminder to anybody here to please type your name in if you can. I saw that Tomas Deli was trying to log in, so I'm gonna put his name in. Okay. So this is what we have. And now, just in the interest of time, I'm just going to go forward and do this. So cosine of 60 degrees is equal to 1/2, and sine of 60 degrees is equal to square root of 3 over 2. So what we get is that A is equal to, well, the square of 1/2. So that's 1/4 minus the square of root 3 over 2, which is 3/4. Then over here, we have 2 times 1/2 times square root of 3 over 2. Here we have, again, 2 times 1/2 times square root of 3 over 2. And then in the last thing, we have sine squared of 60 degrees, which is 3/4, minus cosine squared of 60 degrees, which is 1/4. And if I simplify this out, I get minus 1/2. Here, the 2 and the 1/2 cancel each other out. So I'm just left with square root of 3 over 2. So square root of 3 over 2. And here we have square root of 3 over 2. And here I have positive 1/2. Okay, so this is what we get for the matrix. Okay. And so now it asks what vector is obtained when 1, 1 is reflected over the line. So if we know the matrix and we know the vector, then what do we have to do to get the answer? Well, we're going to have to multiply the matrix by the vector, right? The matrix tells you how to reflect. So if we do this, we get minus 1/2 root 3 over 2, root 3 over 2, 1/2, and we multiply this by the vector 1, 1. And that's the same thing as 1 times minus 1/2 root 3 over 2 plus 1 times root 3 over 2, 1/2. And this is going to be equal to root 3 over 2 minus 1/2, and then root 3 over 2 plus 1/2, which is going to actually be about 0.366 and 1.366. Okay, so this is what we get if we take the vector 1, 1 that kind of looks like this. I don't want to clutter the diagram anymore, but the vector 1, 1 is where my laser pointer is right now. And the other vector where you reflect it is going to be pointing a little bit more upward, a little bit closer to the y-axis. And that makes sense, right? Because the y-coordinate here is much bigger than the x-coordinate. So that means that the vector that we get when we do this reflection here is going to be much closer to the y-axis than what we started with. Okay. All right. So, all right. So any questions about this problem? Yeah, 0.366. Yes.
To me, it's well understood. Thank you for the stuff.
Good. Okay, you're welcome. Yes, so yes, Princeton, it's 0.366. Okay. Any other questions?
Thank you very much.
All right, you're welcome. Okay. All right, so let's just do the third one so we can get to the new material for today. So, well, okay, so maybe I won't go over all of this third one, but we know that if we do a reflection and then we do a reflection again, we go back to where we start, right? If I've got a vector and I'm reflecting it over some line, then if I reflect it and then I reflect it back, it goes back to where we started, right? So what we want to show, what that should translate to in terms of matrices, is that if we take a matrix that corresponds to a reflection and then we multiply it by itself, then we should end up back where we started. So what we need to show here is that no matter what the line is, so for any alpha at all, we have, if you take this matrix, cosine squared alpha minus sine squared alpha, 2 cosine alpha sine alpha, 2 cosine alpha sine alpha, and then sine squared alpha minus cosine squared alpha. And then if you multiply it by itself, so you write the same matrix again, cosine squared alpha minus sine squared alpha, 2 cosine alpha sine alpha, 2 cosine alpha sine alpha, and then sine squared alpha minus cosine squared alpha. You need to show that if you multiply these together, you're going to get 1, 0, 0, 1. Okay, that everything is going to simplify and it's going to give you 1, 0, 0, 1. So maybe I won't do the whole problem, but I'm just going to do maybe the first entry. And then you can do the other ones. So the first entry, meaning top left, when I multiply these matrices together, I get cosine squared alpha minus sine squared alpha times cosine squared alpha minus sine squared alpha, right? That's doing the first times the first over here. And then I get 2 cosine alpha sine alpha times 2 cosine alpha sine alpha. So plus 2 cosine alpha sine alpha times 2 cosine alpha sine alpha. Okay. And so it turns out that if you write this all down, this turns out to be cosine to the 4th alpha plus sine to the 4th alpha, and then plus, this comes out to be plus 2 cosine squared alpha sine squared alpha. Okay, so this is a little bit of an exercise. I skipped a couple of steps here to get to this. And then you can rewrite this as cosine squared alpha plus sine squared alpha squared. If you do this squared, you get exactly this expression. But now what's cosine squared alpha plus sine squared alpha for any angle alpha is always
equal to 1.
Always equal to 1, exactly. So this is equal to 1 squared, and this is just going to be 1. So this shows that the top left entry is 1. Okay? And so to fully do the problem, you then need to just repeat this for all of the other entries. You need to show that the top right entry is 0, and the bottom left entry is 0, and the bottom right entry is 1. So you have to do 4 calculations just like this, but I'll leave it as an exercise to just show that if you multiply these matrices all out, and it maybe gets a little bit complicated, but in the end, it all simplifies down to 1, 0, 0, 1. Okay. Okay, so any questions on this?
Hello?
Hello, yes.
Yeah,
Gabriel?
yeah, Prof. I'm approving some difficulties because I can't see nothing on my screen. I don't know,
Oh,
maybe that
Tomas,
the
okay.
network.
Yeah.
Yes.
So yeah, I don't know how to, I mean, I think the screen is visible, so it's probably on your end with the network. Yeah, so I don't know. I mean, you can always try logging off and logging on again. But in any case, I'll send the notes after class if you need to see the screen. But I don't think I can do much about that. I think it's on your phone.
Okay.
Okay. You're welcome. Okay, other questions? Okay. So, all right. So let's talk a little bit about the new stuff that we're going to do today. So I mentioned this at the end of the last time, but we did all of these examples of a matrix working in 2 dimensions to bring a vector to another vector. And we saw that we saw these examples of reflections and rotations and dilations, all of these geometric things that you can do with matrices in 2 dimensions. So I want to just say a teeny little bit about how you can do matrices in 3 dimensions instead. Now, there's many more cases of what can happen in 3 dimensions. So I'm not going to treat this comprehensively at all. I just want to show a couple of examples. So when we want to do a matrix in 3 dimensions, as I said last time, the matrices are going to be 3 by 3 matrices instead of 2 by 2 matrices, right? And we're not going to treat the subject comprehensively, but instead we're just going to give a couple of examples. But the idea, remember, is if A is a 3 by 3 matrix, and if V is a vector in R3, meaning it's a vector with 3 entries, then AV is also another vector in R3. And A is going to represent, in our examples, some sort of geometric transformation on V. Okay, so we have to think about how do 3 by 3 matrices work. Okay, so I want to just do 2 examples. So one thing is that in 3 dimensions, you can't just say a rotation. If you have a rotation in 3 dimensions, there needs to be an axis that you're rotating around. So you have to specify what's called an axis of rotation. Okay, so let's imagine, and this should say the z-axis. Okay, so let's imagine we want to understand the rotation counterclockwise by angle alpha around the z-axis. So I'm going to draw my XYZ space like this. And then we imagine we want to rotate kind of around the z-axis like this. Okay, so we're spinning the XY plane around the z-axis. Okay, so if we recall, in the XY plane, the matrix of rotation CCW, which means counterclockwise, by alpha was this matrix. It was cosine alpha minus sine alpha, and cosine alpha. So this was our matrix of rotation. So what happens in XYZ space? Well, if I'm given some vector, which I'll call, I don't know, X, Y, and Z, then rotation around the Z-axis, does it change Z? Well, it doesn't change the Z coordinate, right? It doesn't change the Z coordinate at all because we're rotating it around the Z-axis. So everything is staying at the same height. We're not changing the actual Z coordinate. So rotation around the Z-axis, it leaves Z fixed and rotates the X and Y coordinates like in 2 dimensions. Okay, so it leaves the Z coordinate fixed and it rotates the X and Y coordinates like you were in 2 dimensions. Okay. And so it turns out that the matrix that you're going to have for this, I'm going to just kind of tell you the answer. We're not going to do a real derivation. The matrix is going to be the following. It's going to be cosine alpha minus sine alpha, and cosine alpha. And then there's going to be a 1 over here, and then there's going to be zeros everywhere else. This is going to be the matrix of rotation. And maybe let me give you just a quick, why is this the case? Well, the point is, if I take this matrix, cosine alpha minus sine alpha, cosine alpha, and then a 1 over here with a bunch of zeros, and if I multiply this by x, y, z, well, then what do I get? Well, the z coordinate's going to stay the same, right? If I look for the bottom entry, I have 0 times x plus 0 times y plus 1 times z, right? So what I get down here at the bottom is z. Okay. What about the other things? Well, to get my other 2 entries here, well, the top entry is going to be what? Cosine alpha times x plus minus sine alpha times y, which is the exact same thing I get when I looked for the top coordinate when you apply the 2-dimensional version. And ditto, what am I going to get for the middle one? I have sine alpha times x plus cosine alpha times y, and then plus 0 times z, which is exactly the same thing that happens in 2 dimensions here. So I'm going to write this as x prime y prime, where this, if I just look at x prime y prime, this is the rotation of xy by alpha counterclockwise. Okay, so this is sometimes called a block matrix because you can divide the entries up into blocks where the different entries are non-zero or are 0. And so if you have a rotation like this in 3 dimensions, it turns out that what you do is if one of your dimensions is fixed because you're rotating around the z-axis, then the kind of z part of the matrix just gets a 1 down here. And then if the x and y are being rotated counterclockwise, just like they would be in the xy plane, then you have the same matrix that you would have in the xy plane, but you put it up here in the upper left-hand corner of the matrix, and then you fill in the rest with zeros. What this matrix basically does is that it treats x and y separately from how it treats z. And so it rotates x and y by an angle theta counterclockwise, and z it leaves fixed. It doesn't do anything to the z. And the point is, this upper left-hand corner is acting on the x and the y, and this lower right-hand corner, this 1 over here, is acting on the z. And that's not going to change anything. Okay, so this is not a full proof or a derivation, but maybe it's a sketch, and it's hopefully maybe a little bit convincing that this is the correct matrix. This is how you're going to rotate things around the z-axis when you're in 3 dimensions. Okay, so you just take the 2-dimensional rotation matrix, and then you throw in an extra 1 down here, and then everything else is a 0. Okay, so any questions on this?
Hello. I'm just listening to you now because no way for me to see anything. I just waiting for the notes. That's all.
Okay, fine. I will send the notes today, so that's fine. Okay. All right. So this is one example.
Yeah, I'm sorry for that.
Okay, no worries, no worries. Okay, so let's do maybe an easier example, actually. Maybe I should have started with this example. What about the example of reflection over the XY plane? So here I'm going to draw a picture. Again, I have space. Here's X, here's Y, Y-axis, here's the Z-axis. And if I have a vector I want to reflect over the XY plane, So I have maybe some vector v over here. And then I want to take its reflection, which I'll draw in purple, its reflection over the xy plane. This is, reflection of v over the xy plane. Okay. So I want to know what's going to do that. Well, the formula for reflection over the xy plane is not that difficult, right? Oh, this is wrong. Sorry, I need to fix this typo. This should be x, and this here should be negative z. Okay, right, because the x and the y stay the same, and when we reflect over the xy plane, we just have the z coordinate becomes negative, right? The x and the y stay the same, and the z coordinate becomes negative. Okay. So we want to know what's the matrix that encodes this. So here's a question. Maybe one of you can guess it. I want to know what matrix will send x, y, z to this new vector xy minus z. Well, I know that if I just have the identity matrix here, if I just do the identity matrix, well, that's going to send x, y, z to itself. So if all that I want to do is change the z coordinate from itself to a negative number, then what do you think I should do with this identity matrix so that it, instead of sending x, y, z to itself, it still sends x and y to itself, but it now sends z to minus z? So what should we do with this matrix? How should I change it?
Multiply by -1.
So multiply which entry by -1?
The last entry.
Just the last entry, exactly. Thank you, Gabe. So that's exactly right. Right? So we want to multiply this last entry by -1. Right? So this is exactly right. And you can verify for yourself that if you do this product, you exactly get this matrix here. Okay, so this is going to be correct. Okay, again, let me mute. Okay, right, so if I take this matrix and I multiply by x, y, z, I get xy minus z, right? So what this tells me is that this matrix here, this matrix reflects vectors over the xy plane. Okay. And on the homework, you can do something similar for how do you reflect over the xz plane and how do you reflect over the yz plane. Okay, questions on this example? It's maybe a little easier than the previous example. Okay, and so I should say that, of course, there's, this is just scratching the surface, right? I mean, you can reflect over planes that are not parallel to the coordinate planes. So you can reflect over diagonal planes. You can rotate with diagonal axes of rotation. There's all sorts of other linear transformations you can do in 3 dimensions where you stretch things in certain directions and stretch them by a different factor in another dimension and then rotate it around. So there's really a huge library of geometric matrix transformations in 3 dimensions. But I just wanted to show you 2 of the most basic ones, where you reflect over a coordinate plane and where you rotate around a coordinate axis. Okay, so if you're interested in studying 3-dimensional geometry, then there's a lot more that you can do here. Okay, but I just wanted to show you how it works in 3 dimensions, which is the same principle as 2 dimensions. There's just always going to be a 3x3 matrix instead of a 2x2 matrix. Okay, so let me really cross this out so that we know there's no negative sign with the x over here. Nothing there. It's just a regular x. Okay. Okay, so let's do, for the last 15 minutes or so, I want to introduce this new concept.
Yes, sir.
Oh, yes, question. Yes. Prince?
Yeah, we did diagram that you do for X, Y, and Z.
Mm-hmm.
Yeah, will the position of these letters be constant or it changes anytime?
So this is the convention, is to always draw the axes like this. Okay, So of course, since it's 3 dimensions, if you're looking at it in a different way, the axis positions might look different. But the general mathematical convention is to always draw the axes like this, with z pointing up, y pointing to the right, and x pointing kind of, the idea is that x is supposed to be pointing out of the paper. But to create that impression in 2 dimensions, we draw this diagonal. But what you should be thinking is z points up, y points to the side, and x is pointing out straight at you. But this is basically always how it's drawn.
Yeah, because our thinking on, I think like the y will point up where the z point as to where y is belong. So
right. I mean, that's also completely reasonable. There's no reason why this convention is better. It's just the way it's always done. So usually people have the z-axis pointing upward. There's nothing wrong. It's with doing it a different way, and these formulas won't change if you do it a different way. But if you do it a different way, it just won't look like what other people are assuming. So people generally assume that the z direction is the vertical direction.
Okay, thank you.
Okay, you're welcome. All right, other questions? Okay. Okay, so let's, for the last 10 or 15 minutes, let's start this a new concept, which will be easier at the start. So it's going to be calculational. So to any square matrix, so there's something called a determinant. And so I'm just going to mention what a determinant is today, but next week we'll talk about, you know, what it means and how you calculate it and why it matters. Okay, but today we're just going to define it. So if I have a square matrix, so it has to be a matrix where the number of columns is the same as the number of rows. Okay, so if I have a square matrix, then every square matrix has a number called its determinant. And what we're going to do today is we're going to give formulas for how to calculate this number to the determinant. But next week, we'll talk a little bit more about what it means. Okay. So, and we're going to do it, you can do it for any square matrix, but today we're going to be doing it for a 1x1 matrix, a 2x2 matrix, and a 3x3 matrix. Okay. So for a 1x1 matrix, just has one entry, A, then the determinant of the matrix is just A. So it's a 1x1 matrix, the matrix is 5, then the determinant is 5. Okay, 1x1 matrix, the matrix is just the determinant. So for a 2x2 matrix, A, B, C, D, the definition of this determinant is you multiply A by D, and then you multiply B by C, and you subtract them. Okay, so this is what's called the determinant of the matrix A, B, C, D, is given by the formula AD minus BC. So if we have an example, if I have the matrix 1, 3, 7, 9, and I want to calculate the determinant, I multiply, you know, A and D, so the top left and the bottom right entry, that's 1 times 9, which is 9, right? This is 9. And then I multiply the top right and the bottom left entry, that's 3 times 7, which is 21. And then I subtract them, and I get the determinant, which is negative 12. Okay. And so just a matter of notation for the determinant, we would write here either that determinant of 1739 is equal to minus 12, or you can also do the following. If you write the matrix, but instead of using parentheses or square brackets, you just use lines. So I write it like this, 1379 with just lines and no brackets and no parentheses, then that actually means determinant. So you could write this 1379 equals minus 12. So when I just use straight lines, that means determinant. Okay. So if I just use straight lines, that means the determinant. Okay, so 1x1 and 2x2 matrices, determinants are pretty basic. All right, any questions on this?
No,
Sure.
no, I just see the screen now.
Okay, oh, you can see it now. Okay,
Yeah, yeah, yeah.
okay, good. Okay,
No,
so,
no question.
okay, great. Okay, so I want to finish by talking about 3x3 determinants, which are a little bit more complicated. So if I have an arbitrary 3x3 matrix, I can write it like this: A, B, C, D, E, F, G, H, I, right? And then what I claim is that I have a somewhat more complicated formula for the determinant, right? So in fact, we have this formula is given by this expression here that's very difficult to memorize. So the determinant is going to be AEI plus BFG plus CDH minus AFH minus BDI minus CEG. So much, much harder to memorize than AD minus BC. But there are several ways to remember this, and today we'll talk about one of them. If I write down the matrix A, B, C, D, E, F, G, H, I, and then what I do is I'm going to write down the first two columns again. So A, D, G, and then B, E, H. So I'm just going to repeat, the first two columns. And then what I do is I'm going to draw all the diagonals that go in one direction, that go down and forward, and I'm going to write little pluses there. And then I'm going to draw, do purple, so I'll draw all the diagonals that go in the other direction. All the diagonals that go in the other direction, and I'm going to write minuses there. And then this will give the formula, right? I look at all of the diagonals that are going in the positive direction, and I have AEI, BFG, CDH, right? So the pluses tell me to add them, right? AEI plus BFG plus CDH. And now I look at everything going backward in the minus direction, and the minuses tell me to subtract them. So I have CEG, AFH, and BDI. So minus CEG minus AFH minus BDI. Okay, and that gives me the formula for the determinant. Okay, so it's one way. I mean, I don't expect anybody to actually memorize this. I haven't memorized it, but I know how to rederive it by doing this little trick. You write everything down, and the forward diagonals get added, the backward diagonals get subtracted. Now, it turns out there's another way of figuring this out, which is called expansion by minors, which we'll talk about next week, but we're not going to do that today. Okay, but this is the formula for the determinant of a 3x3 matrix. And if you had a 4x4 matrix where you'd have 16 entries, so you'd have to have the letters A all the way up through P, then you would have some horrible formula where you'd have 24 different terms, and each one would be a product of 4 different entries. So really a completely unmemorizable formula. Maybe if you study, you can memorize this formula, but the analogous formula for 4 dimensions is completely impossible to memorize. So we'll have methods in general that will work for any kind of determinant. But for us right now, the most important examples are going to be 1x1, 2x2, and 3x3. So this is the formula for a 3x3 determinant. Okay. And so we should do an example to just make it a little more real. So for our example, I want to calculate the determinant just of this matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So what do we get? I'm going to just use the trick, right? So the trick is I write 1, 4, 7, 2, 5, 8, and 3, 6, 9, and then I write the first 2 columns again. So 1, 4, 7 again, and 2, 5, 8 again. And then I'm going to circle my diagonals. These all get a plus. And then I'm going to circle the other diagonals in the opposite direction, and these all get a minus. Minus, minus, minus. And so what I get is 1 times 5 times 9 plus 2 times 6 times 7, plus 3 times 4 times 8, minus 3 times 5 times 7, minus 1 times 6 times 8, minus 2 times 4 times 9. And let's just do this, right? We can do all of this. It's worth calculating this out. So 1 times 5 times 9 is 45. 2 times 6 times 7, that's 42 times 2, that's 84. 3 times 4 times 8, that's 3 times 32, which is 96. Then minus 3 times 5 times 7, that's 3 times 35, which is 105. So minus 105. 1 times 6 times 8 is 48. And 2 times 4 times 9 is 2 times 36. So that's 72. Okay, and so let's see what we get here. So 45 plus 84 is 129, and then plus 96 is going to be 225. And then minus, well, what is 105 plus 48 plus 72? Well, 105 plus 48 is 153, and then you add 72, and that gives you 225. So we get 225 here. So the actual answer to this determinant is 0. After this big complicated calculation, the determinant just turns out to be 0. Okay, which is kind of great. It turns out that this is not a coincidence. The determinant being 0 really has a meaning. We're not going to see it so much this time, but if you go back to the 2x2 case, if you remember, we talked about the inverses of 2x2 matrices before, and the inverse had this step where you had to divide by AD minus BC. You had to divide by the determinant. And so, and if the matrix was invertible, if it had an inverse, that was the same as this determinant not being 0. Well, it turns out with 3x3 matrices, there's a similar formula, but it's more complicated. But the idea is the same, which is that the matrix is going to be invertible exactly when the determinant is not 0. So I'm not going to prove this right now. I'm just going to state this as a fact. A 3x3 matrix is invertible exactly when the determinant is not 0. Okay. And so since this determinant is 0, so we conclude that this matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, we conclude that this is not invertible. Okay. Conclude this matrix is not invertible. Okay. And so, so we conclude this matrix is not invertible. And that is, not so clear by looking at it, right? I mean, it's not so clear that any of this is true. I just kind of gave you a formula. We're going to see a little bit more why this formula makes sense and what it means. But for now, all that we know is that the determinant of this matrix is 0. So are there any questions on this example?
No, yes, okay.
Okay, it's okay. Okay, so all right, so that's good for the new material for today. So there's a couple of homework questions that I'll give. So the first one is if a vector, we did this already for the XY plane in our example. So I want to ask you the same thing. So if you reflect a vector XYZ over the XZ plane, what's the result? And then once you know that result, what's the matrix that's going to give you the correct reflection? And now do the same thing for the YZ plane instead of the XZ plane. And then the last one is a question about determinants. What's the determinant of the 1x1 identity matrix I1? That's just 1. What about the 2x2 identity matrix? What's its determinant? And then what's the determinant of the 3x3 identity matrix? Okay, so hopefully you'll see a pattern here. So these are the homework questions, which you'll have when I send out the notes. And then So this is thank you for your attention. And so what we're going to do next week is we're going to talk a little bit more about determinants. And then we're also going to define what's called the cross product of two vectors. And it turns out that cross products and determinants are related. And the cross product is something that's very important in physics. Okay, so the cross product shows up a lot of times when you're trying to understand anything in the physics of rotating bodies. So first of all, some equations in electromagnetism can be phrased in terms of cross products, and then also like torque, so the amount of energy that it takes to twist something. This is also expressed in terms of cross products. So we're going to define cross product of two vectors next week, and we'll show how it's related to the determinant. Okay. So thank you again for your attention. And a reminder, please, if you have not yet written your name in the chat, I think most people have, but if you have not written your name in the chat, please do so that we have a record of your attendance. Okay, any questions? Oh, and our guest. Yes, we have a guest. Asumana, do you want to introduce the guest?
Yes, I want to do that. And I want to say thanks to all the teachers. You are the one that making us do the things we want to do for Liberia. And visiting us today was actually introduced to me by one of your teachers, Ms. Asta Kaba, and who is a math teacher. And but she's not doing well now. She is in the state. So she wanted for Honorable Tianwan Gwenklo to observe this class. And Honorable Gwenklo is from Nimba County. So Honorable Gwenklo, if you are listening, would you like to say something to us? Honorable Gwenklo, if you are listening, would you like to say something to us? Okay, probably, okay. Anyway, he is from Sanikole. He was human rights lawyer.
Listen, I was muted.
Oh,
okay.
I just sat here today and really enjoyed this class. Of course, I was a poor math student in high school, so I'm watching all this sine, cosine, and I'm confused. But what I enjoy is that there is a way out to strengthen our capacity in Liberia, that actually someone can sit in the United States here and teach people in Liberia. I want to thank the professor very much for providing us that opportunity to strengthen our math teachers. That's the first thing I want to say thank you. And I want to thank Brother Asumana Jabate for, asking me to come on this program. It was not a time wasted at all, even though I didn't understand half of what was being said, but I enjoyed the fact that our capacity in Liberia can be built from abroad. So as someone who's running for the presidency of Liberia, at least I will remember this. I have a few days in America to go back, and I will speak about this, that we can really strengthen math teachers in Liberia, English teachers in Liberia, science teachers in Liberia, by entering into relationship with people who have better knowledge of this from abroad to strengthen our teachers. This is a very good continuing education approach. So I want to tell you, thank you very much for this class. And I want to thank the students, those who took the opportunity to attend this in Liberia. Please persuade many of your colleagues in Liberia, Prince, all of you, and Francis. I saw you people asking questions. You show much interest And I see that Joyce Yahweh is the only lady on this platform. I hope we can get more ladies to come on this platform. So I want to tell you, thank you very much. That's what I want to say. And thank you, Jabate.
And thank you. And teachers, thanks very much. I'm very proud of you. And let's keep it up. This is our Honorable Gonclo. This is our second year. And hopefully we'll be strong enough to carry for 5 years. And we need your assistance to spread the word to other people that want to observe. And the more observer we get, the better it is for us to continue to strengthen our education sector in Liberia. So share the information for us. And Dr. Albers, thank you from the bottom of my heart. And for the 3 times you have been to Liberia, it meant a whole lot to me. And so thank you again. And Sanjay from the Ministry of Education, thank you. And Mr. Boplo from the Ministry of Education. Yeah. So all of you guys continue to support us, okay? Have a nice time and continue to do the homework. Okay, bye-bye.
All right.
All right.
All
Thank
right,
you.
Professor Obos. The day you come to Liberia, you have any legal problem, I'll give you free legal service, okay?
Thank you. Thank you. Hopefully I won't need any.
Okay.
All right. Thank you. Thank you for observing. I really like having observers here. So I appreciate you being here.
Okay. Thank you.
Okay.
All right. Thank you so much, sir.
All right. So everybody have a good weekend. And I will send the notes later today on the WhatsApp chat room. Richard, I'll get your phone number added. I think Sange controls the chat room, so I'll send the number to Sange and I think she can add it. And then and I'll get the recording and the notes to everybody later today.